G'day, in this video we're going to continue looking at series and parallel circuits. Our focus is looking at resistance in series and parallel circuits in particular, and how the resistances of components that exist in series or parallel will result in total resistance in the circuit. So our learning intentions today is to apply Ohm's laws to series circuits and Kirchhoff's voltage law, as well as to parallel circuits and Kirchhoff's current law, to be able to prove where these two equations actually come from. And then from there, we'll do a quick practice question to apply some of our knowledge. So in a series circuit, we know two key things. First off, Kirchhoff's voltage law states that V total should be equal to the sum of all voltages across all of our components. In this case, there should be three voltages. So we could have voltage 1, voltage 2, and voltage 3. We also know that I, the current, should be constant. So what that means is in all parts of the circuit, the rate of flow of charge should be equal. Now, Ohm's law states that V is equal to IR, or if we were to rearrange for the resistance of the entire circuit should be equal to the total voltage of all of those components divided by the current. Now we can bring in our Kirchhoff's law here to rewrite this expression as V1 plus V2 plus V3 all over the current. Now because we have a common denominator I, what this means is that we can split each of the voltages on the numerator into three separate fractions that should look like this. Now again, if we were to apply Ohm's law, what this means is V1 over I is the resistance of component number 1, V2 over I is the resistance of component number 2, and V3 over I is the resistance of component number 3. What this means is that the total resistance across the circuit in all of the components that are in series are simply just the sum of each of those resistances. Now to prove this concept, I want you to try and do this one yourself, but imagine that we have a circuit where the current is 0.5 amps. The voltage for component number 1 is 2 volts, component number 2 is 3 volts, and component number 3 is 4 volts. What I want you to do is have a go at applying Kirchhoff's voltage law to calculate the total voltage, apply that to try and calculate the total resistance, then also apply Ohm's law to calculate for the resistance of all of the components. Things get a little bit different, however, when we start looking at components which are parallel in the circuit. Here we need to start applying Kirchhoff's current law. So for a parallel circuit, the total current in the circuit, the sum of each current which passes each individual pathway. As well, we should be assuming that the voltage in the circuit is constant. Again, applying Ohm's law that V is equal to IR, we'll rearrange to make R, the resistance of the entire circuit, RT, be equal to the total voltage over the total current. Now in this situation, because V is constant, V is going to be the same for each of the components. However, I total, if we apply Kirchhoff's current law, can be rewritten as I1 plus I2 plus I3. Now this formula is a little bit trickier to work with because we can't split a fraction into individual sums or individual components when we do not have a common denominator. What this means is we're going to take a reciprocal of each expression in the equation so that we do have a common denominator. So I'm going to rewrite this equation as 1 on RT is equal to the total current over the total voltage, which is equal to the sum of all of the currents divided by the voltage that's in the circuit. Now what this gives us is that 1 on RT is equal to I1 on V plus I2 on V plus I3 on V. Or if we would apply Ohm's law again, that would be 1 on the resistance of component 1 plus 1 on the resistance of component 2 plus 1 on the resistance of component 3. Now, assuming that we have a 12-volt circuit and the following currents are given, I'd like you to take the time to play around with some of these equations, substitute them in to prove that these rules, this series, and these formulae actually work. What I'm going to do to finish off this video is a couple of practice questions where we're going to calculate the total voltage, current, and resistance for all components in the following circuits. In the first question, we're going to look at a circuit power with a 12-volt battery containing a 12 ohm, 4 ohm, and 6 ohm component, which are in series. In the following question, we're going to have the same components with the same resistances as well as the same battery, except everything's going to be wired in parallel. Let's do the series one first. What I'm going to do to begin with is just record all of the relevant data that we've been given so far. Given the data that we've been provided, I'm going to use our resistance series first to try and calculate the resistance of the circuit. This is 12 ohms. Now, we don't have any data about the current of the circuit, but with the data that we have and have calculated so far, it's something that's actually quite easy to find. We can assume, as always for a series circuit, I is going to be constant. And that if we know that V total equals I of the circuit, I total, and R total for the circuit, we can rearrange to calculate for the current. And for this circuit, we know that the current is equal to 1 amp. Now, because we know that the current for the circuit is 1 amp, and that means that 1 amp will be flowing through each of the components, we now know R and I for each individual component. Because we know R and I for each component, we can calculate the individual potential differences across each of those components. If we were to apply Kirchhoff's voltage law, then we know that the voltage in the entire circuit should be equal to the sum of voltages of all components, which equals 12 volts, which matches the information given to us at the beginning of the question. Again, for the second question, we've been given the same components as well as the same power supply, except all of these components have been wired in parallel. In this circuit, we can assume immediately that V is going to be constant, not current. So that means that for any calculation where we have V, the voltage should be equal to 12 volts. This gives us a pretty solid start for the beginning of the question and should allow us to calculate IT pretty quickly. We know that IT is going to be equal to the sum of all of the currents. So if V is equal to IR, then I of one of these components is going to be equal to V divided by the resistance on the component. And this gives us the total current for the circuit. By applying Ohm's law, we should then be able to calculate the total resistance across the circuit. That gives us 12 over 11 ohms. This isn't the only way that we can calculate it though. We can also use our resistance series to prove that we can attain the same value using a slightly different method. So when comparing our results for both of these practice questions, we should notice that the resulting voltages and currents throughout the circuit, as well as the total resistance across the circuit, are quite different despite using the same components. Again, this comes down to the way in which the circuit is being wired, and we'll break down some more of those distinctions in more detail when we get to class. Thank you very much, everyone. In the next video, we'll begin the third and final inquiry question for this module, which looks at magnetism. And the first video will focus on some qualitative properties of magnetism and magnetic objects. Until then, have a good one.